credit David Koo for his insistence years ago that we should be focusing on the central properties of galaxies. So this is a new parameter, which now many of you have heard about. It's sigma 1, the central stellar density projected within 1 kpc. And this is a plot of what sigma 1 looks like in Sloan galaxies versus stellar mass. This is a product of a paper by Jerome Fang several years ago now. And you can see that this parameter, sigma 1, has something to do with quenching. Red sequence and green valley galaxies are here on this ridgeline, and blue cloud galaxies are below. And so something in this direction should make you think of losing gas and quenching. But in addition, we also have a relationship that sigma 1 scales the central velocity dispersion to the power 2, and that also should make you think of black holes from the black hole sigma to the fourth relation. So that's what my talk is going to be about. It's going to be discussing the roles of black holes in quenching galaxies. Now, the thing that really got our attention was not only this diagram at Z of 0, but the fact that it replicates so well to higher redshift. This is from Guillermo Barro's paper, now just published. And same diagram. What really stands out is that the morphology is preserved, but the whole pattern moves down, fitting independently ridge lines to blue and red galaxies at different redshifts gives exactly the same slope at all redshifts, and the separation remains constant. However, both ridge lines move down by about 3/10 of the dex over these redshifts. So I'm going to jump forward to some conclusions. These are some observations that are matched by this power law model. By construction, the power law nature and slopes of those quenched ridge lines in sigma 1 stellar mass and black hole stellar mass are matched. And the evolution of the ridge line 0 points versus time are matched. They're put in by hand. But here are some new things that come out that are not put in by hand. Okay, we'll try this. The location, the lower mass limit of the green valley at 10 log mass equals 10 is matched. The width of the green valley, a whole dex or more, is matched. The slope and 0 point evolution of the star-forming galaxies out of Vanderbilt 2014 is matched. Why the blue and red populations evolve together, why their 0 points go down by 3/10 of a dex over those redshifts, both of them the same, is explained. And we also develop a working scenario for how and why galaxies quench. Assumptions of the model. Dark halos are the scaffolding for galaxy evolution. They determine stellar mass and effective radius, and they provide a clock for when things happen. That's very important. Everything I say by virtue of models here applies only to star-forming galaxies before they quench. So we get M versus virial mass from abundance matching. We get effective radius versus virial radius from abundance matching and also some data. Both of those things say, very important, that effective radius is proportional to virial radius. We assume but also show that 3 structural spacings are actually the same space. One is sigma 1 versus M star. Another is effective radius versus M star, and finally black hole mass versus M star. So if galaxies evolve along a track in one of those spaces, there's a mapping that you can use to get the track in the other 2 spaces. Quenched ridge lines are formed when galaxies pass over a quenching boundary or a Q boundary and stop making stars. The sigma 1 mass ridgeline shows the slope of this boundary. Same diagram I just showed you. Here's the quenched ridgeline, and the boundary at which galaxies are presumed to start quenching is downset by 2/10 of a dex. based on some information. So you can think of some evolutionary track passing over this boundary and beginning to quench. This is rather like a model by Van Dockum, which he presented in cartoon form. This is effective radius, stellar mass. Galaxies evolve along a slope and hit a boundary, and the boundary moves with time. But there's some things that are not so great about this model. He assumed that sigma was constant on the boundary, and you can see that that wouldn't be right because it would predict to first order that all quenched galaxies would have the same sigma, and they do not. Another thing that wasn't explained was why the quenching boundary was sigma and why it moved with time. Those are things that we're going to explain in the toy model. There are 3 power laws with exponents and 1 evolving 0 point in the model. One power law is the stellar mass-halo mass relation, which has a slope S from abundance matching given by 1.75. We're going to assume that black hole mass scales with sigma 1 to some power v, star-forming galaxies only, and we're going to assume a quenching condition. This quenching condition is a little bit different from what you normally see in quenching models. I'm talking here about maintenance mode, which equates a black hole energy rate with a cooling rate from a halo. We don't use rates. We tried that, didn't work. Didn't have the right behavior versus redshift. Something much simpler here. The total working energy coming out of the black hole is equated to some energy heating requirement in total from the halo. So the usual formula here on this side, and then this is assumed to be a power law of virial mass with power T, and there's an evolving 0 point. The 0 point needs to evolve because of the 0.3 Dix evolution in the ridgeline of the quenching boundary. Now, you can show that these things are equal to these things. We won't derive that here, but that means that we need 3 numbers, S, V, and T. We have 3 observations from 2 ridgelines and S, and we observe the 0 point of the boundary to move, and we fit that by hand. And so that gives us the values of T, V, and S, and also the 0 point motion of the boundary. Now, just to convince you that sigma 1 mass maps into RE mass, here is a plot versus redshift. Each one is the panel M star versus effective radius. SMA is effective radius. And the points are colored by sigma 1, and you can see that there are stripes there. By the same token, this is sigma 1 versus mass, and the points are colored by effective radius, and you can again see stripes. And so you know when you see stripes like that, you're looking at a plane in a 3-dimensional space, and here's the equation of the plane. Sigma 1 goes as inversely as RE and positively as mass. Okay, so I've said that this space maps onto this space and shown you an example there. Blow it up. That means that these are contours of constant sigma 1. So galaxies, as they evolve along some trajectory, evolve to higher levels of sigma 1. But because black hole is a power of sigma 1, that exponent V, that means that black hole mass is also evolving along this trajectory. In other words, we can read off a black hole mass just from a position in this diagram. And it's not a small effect. This range from top to bottom of the cloud here is a factor of 17 in black hole mass. So the one new thing that's really novel in this toy model is the notion that black hole mass depends on galaxy radius as well as galaxy mass. And we examine the consequences of that. Now, the fact that black hole mass depends on galaxy radius is not new. Brian showed us this beautiful figure here, and people have analyzed these data. There's a paper by Remco van den Bosch, and this is a lousy relationship. But Remco showed that you can make it a nice tight relationship. You can restore the ridgeline if you introduce a term that's a function of radius. These are large RE galaxies, these are small RE galaxies. This is called the black hole fundamental plane. And just to further convince you that this space is really the same as this space, just look at this, okay? So this region covers this region. Here's the ridgeline, and here are the star-forming galaxies below. Blue is star-forming, quenched up there. Same pattern, same morphology. Now, the evolutionary paths in this model come from knowing the effective radius, which scales with in proportion to the virial radius. And when you work out the mathematics of that, you find that these trajectories are nearly parallel to this Q boundary. This is the Q boundary that came from looking in the other diagram, sigma 1 mass, and using the mapping to get it into this. And it has a slope of 0.44, not 1, which is what constant sigma would give. Constant sigma would give a line like this. This is much more inclined. And that's very important because remember that these objects here have lower black hole mass than these. And because this boundary is so inclined, they have to evolve a very, very long way in order to get a black hole mass that's big enough to quench. So this is why the Green Valley is as wide as it is. It's because we have a range of black hole masses and a quenching boundary that is inclined. Yes, shallow Q boundary. Okay. Moving on. We have these two terms, E heat and E black hole. Just to remind you what they are. This is the total mass, total energy emitted by a black hole during its lifetime. And this is some quota that the halo needs in order to quench. There are 3 different masses here. This is a big galaxy today. This is a little galaxy today. E heat just depends on the halo mass, so it's 1 line. But E black hole has a range reflecting the range of black hole masses in a mass at this redshift. So a galaxy quenches when its black hole approaches from below, but then crosses over this line. So these are the quenched objects. And interestingly enough, we've just put in this empirical formula for E heat, but actually the thermal content of the halo today is just about, of this mass, is just about 10 to the 61 ergs. And so therefore it may be that, in fact, this term here is a match to the total thermal content of halos as a function of time. We have to work that out. Okay, here are the predicted patterns in our diagrams. Let's start with sigma 1 versus mass. We put in the slope and the 0 point, so there's no doubt, it's not a mystery, that our quenched galaxies, which are these little open circles, perfectly overlie the boundaries that are observed for the quenching line. That was put in by hand. However, the galaxies actually reach the ridge line right here at 10 to the 10th solar masses, and do so at each redshift. They come into the Green Valley here, but they have to evolve a little bit more in order to actually become quenched. So our quenching regions would start here, right where the red line starts. Now, a very interesting point is, why is this lower limit, not only is it in the right place, but it doesn't evolve with time? That's equivalent to saying that the mean mass in the Green Valley doesn't evolve with time. The reason why this is happening is because if you actually quench in the right place at one redshift, you will always do so at every other redshift. Why? Because this line is moving down, and this is a miracle, a fluke, a complete coincidence. The cloud of evolving star-forming galaxies is also moving down. And they are moving down for 2 different reasons. First of all, this is the quenching boundary, and that has to do with the physics of quenching. This cloud of galaxies that's approaching the quenching boundary Its radius, and therefore its sigma 1, is set by the radius of galaxies, which depends on the radius of halos. And so the location of these galaxies in this plot and this plot is governed by halo physics. Two completely different sets of equations, and as far as I can see, the motions, the parallel motions, is just a total coincidence. Let me say a little bit more about how galaxies actually quench in this model. Each point here is a simulated galaxy, and it has a tail. And the tail shows you the most recent motion that it exhibited in getting to that particular place. So it was here, it moved there. The purpose of showing the tails is to emphasize my statement. Galaxies actually, another fluke, evolve almost parallel to the quenching boundary. So an interesting conclusion here is that if the boundary did not move with time, galaxies would not quench. This object would keep going forever. In fact, what happens with time is that this boundary is coming down because of the evolving 0 point that we built in to E heat. It's like a guillotine. I'm evolving and suddenly, pow, something cuts me off as this boundary overtakes me and causes me to quench. So my original picture, our original picture, was that we'd see inclined lines here and galaxies would cross boundaries. But actually, no, it's much more that the boundary crosses the galaxy. And so even though I do say in this model that it's a contest between galaxies and their halos, black holes and halos, actually what's happening is that the halos are getting weaker with time and it takes less to quench them. And so, yes, black holes win the contest, but not because they're particularly strong, it's because the halos are getting weaker with time. One more comment about this. These gray regions here are meant to illustrate the regions that are populated by the Van der Waals star-forming galaxies, showing plus or minus 1.5 sigma in radius that he measured. Now, this model has a problem, which we haven't solved, and it creates too many massive galaxies, especially at late times. There aren't very many galaxies up there. Maybe it's a counting problem. We haven't actually tried to calculate number densities, but we do predict that galaxies should get to this point, and I think there are very few such objects. So that needs to be looked into. Maybe there's another quenching mode that comes in when galaxies get very massive. I don't know. Okay, so this was the simplest possible toy model you could possibly imagine, a bunch of power laws, and as yet very little physics in it, very phenomenological. But if it's true, there are some important insights. So the first is that galaxy quenching is neither pure AGN or halo quenching. I hear people use those words all the time. It's a trade-off between the two, a contest between the black hole and the halo, and finally, the black hole vanquishes the halo just because mainly the halo gets weaker. Galaxies evolve nearly parallel to the Q boundary, and this produces a very wide green valley. Galaxies almost do not quench. They only quench because halos are easier to quench at late times, and that's this term K of Z. I haven't talked very much about it, but the dark matter halo formation theory actually explains the blue galaxy ridgeline slopes and 0 points if you imagine that effective radii are proportional to virial radii. Now, we've seen that the same picture seems to exist at all redshifts, and so that tells us that the same basic picture of quenching must apply at all redshifts. It's always black hole versus halo. As I've explained, the matching motion of the red and blue galaxy groups is a fluke. It's because the ridgeline moves down due to the halo change, and the star-forming galaxies move down due to the change in their radii that comes out of the dark halos. It could have been differently. And in fact, what we're seeing now, Sandra talked about this, is that they don't exactly match. And so what we're detecting now is structure on the ridgeline because the old galaxies are not keeping up with the newly quenched ones. Okay, a time clock in the model comes from the dark halos. The dark halo physics allows you to say when this happens, at what redshift, etc. And it determines R and mass as a function of time. You need this diagram as the bridge between dark halos and black holes. The halos by themselves in principle say nothing about the black holes. You need the central properties sigma, and you need the mapping between sigma mass and RE mass in order to make that bridge. And my last point here is that more general comment. I really think now, thanks to abundance matching and various other observations, putting a clock on galaxy formation and also providing us with radii, we're getting a much more accurate picture now of how galaxies actually evolve. This combination is answering basic questions, including how to link progenitors and their descendants, what the structural relations look like as a function of time, how the star formation rate depends as a function of time, a clock, etc., etc. So a bigger implication is that if the model is correct, maybe its assumptions are correct, and those assumptions can be used to calculate other things. Thank you.
Do you think it is valid also in the supernova regime, in the small masses regime?
That's an excellent question, and it also relates to Richard's talk and whether or not there is a phase that of more rapid black hole growth. If you just use the exponents in this formula and the rate at which objects move here, you show that black hole growth is just about proportional to stellar mass growth along the star-forming track. Whereas Richard was showing us that there would be some point in here, and it would be interesting to reparameterize your results in this picture, at which there would be a pickup. First of all, I will say that as far as the validity of the model is concerned, we don't need to know what's going on here when the holes are small. The formula is used to calculate the boundary. So all we need to assume is that the black hole growth rate near the boundary is as we have said. Okay? Now, with regard to your statement, I think you would like to know if black holes are really growing according to the formula, or whether or not they're killed by supernovae when they're small, because star formation would dominate there. And I think it's very possible. So if there's one thing wrong with this model, it's probably the assumption that black holes grow at the same rate regardless of what their star formation rate is.
Regarding the mapping between sigma 1 and black hole mass star formation rate, the plot that you showed with Brian's plot of black hole mass where the separation versus and a star that could show that it's very similar to sigma 1. I wanted to point out that actually it's not quite the same because there are lots of star-forming galaxies in the ridge line, and whereas in when you substitute with black hole mass, the separation is much cleaner. And so, in other words, the SSFR for the sigma 1 diagram is an L shape, but when you replace sigma 1 with black hole mass, it's a straight line. I'm wondering if you can comment on why that might.
Right. I alluded to it. We're finding structure in the ridgeline, and the overlap of star-forming galaxies onto the ridgeline is at least in part caused by the fact that galaxies are moving and evolving. So you're mixing together different generations at different times. The problem is the model predicts the existence of big star-forming galaxies. So the existence of big BCGs, so that's not a problem, they're quenched. The problem is that the model wants us to have lots of big star-forming galaxies. The halo is already in the model. Yes?
When you say the halo gets weaker compared to how strong the black hole gets, is it just the rate of
No, it's the statement that at two different redshifts have halos at a given same mass. At the lower redshift, more recent times, the heating quota for that mass halo is less. Yes, and there could be something in the structure of the halo that would help to explain that. And also the fact that that same mass halos are becoming, their cold streams are lessened with time because inflow rates are lower. So the sign of the effect is plausible. Well, I should look at that, but in work that I didn't have time to show you, we redid all of this in the context of M dots. It doesn't work. Does not give the right morphology of these diagrams as a function of time. So we spent months worrying about that, trying to make it work, and said, heck, let's do something really simple, and just fell out like a charm.
Thank you. All right, good afternoon, everyone. I'm going to continue with the trend of talking about HN and